Today we are going to learn about real-time streaming with Spark Structured Streaming. You will discover how to set up and process streaming data using Spark Structured Streaming API.
Welcome to our session on real-time streaming with Spark Structured Streaming. In the world of data-driven applications, real-time analytics is not just a luxury but a necessity. Spark Structured Streaming enables us to handle massive data streams efficiently and effectively. Today, we'll dive deep into setting up a Spark streaming application, understanding various streaming sources and syncs, and much more. By the end of this video, you'll have a robust understanding of how to process real-time data using Spark's powerful Structured Streaming API. Let's get started.
Structured streaming is an advanced stream processing engine built on the Spark SQL engine. Unlike traditional batch processing, where data is processed in distinct, separate batches, structured streaming processes data in a continuous manner. This allows for real-time data analysis, providing timely insights and enabling quick decision-making. One of the key advantages of structured streaming is its ability to treat streaming data as an unbounded table, continuously being appended with new data. This approach simplifies the streaming process and provides a unified API for batch and streaming. Common use cases include real-time fraud detection, live data feeds, and dynamic content recommendations. The architecture of structured streaming revolves around sources and syncs, where data is ingested from sources like Kafka, and results are output to syncs like databases or dashboards. Understanding this architecture is crucial for creating efficient streaming applications. To set up a Spark streaming application, the first step is to ensure that you have all the necessary prerequisites installed, including Java, Scala, and Spark itself. Once your environment is ready, you need to configure your Spark environment variables correctly to point to the installed directories. The next step involves creating a Spark session, which is the entry point for all Spark functionalities. This requires specifying configurations like app name and master URL. With the environment configured and the session created, you can start building your application. Begin by defining the input data source, which could be from files, Kafka, or other supported connectors. Then, define the transformations and actions needed to process the data. Finally, specify the output sink where processed data will be written. Testing and running your streaming application involves submitting it to the Spark cluster and monitoring its execution. This hands-on setup provides the foundation for more complex streaming applications. In Spark Structured Streaming, sources are the origin points from where streaming data is ingested, while sinks are the endpoints where processed data is outputted. Common streaming data sources include Kafka, Kinesis, file systems, and socket connections. Each source has its own set of configurations and APIs to facilitate data ingestion. On the other hand, popular data sinks include file systems, databases, and messaging queues like Kafka. Configuring these requires understanding the data formats, connection parameters, and handling of offsets or checkpoints. For instance, when using Kafka as a source, you need to specify the Kafka broker details, topic names, and offset management strategy. Similarly, writing data to a database sink would involve specifying JDBC connection details and table schemas. Real-world examples of sources and sinks include ingesting social media feeds from Twitter as a source and outputting sentiment analysis results to a dashboard as a sink. Mastering the setup of sources and sinks is crucial for building robust streaming solutions. Handling late data is a common challenge in real-time streaming applications. Late data refers to data that arrives after its expected event time, which can skew results if not handled properly. In Spark Structured Streaming, distinguishing between event time and processing time is essential. Event time is the timestamp when the event occurred, while processing time is when the event is processed by the application. To address late data, Spark provides a watermarking mechanism, which allows you to specify a threshold for late data tolerance. This ensures that only relevant data within a certain time frame is considered for processing. Window operations, such as tumbling and sliding windows, are also vital for aggregating data over specific time intervals, taking late data into account. Implementing these solutions in Spark involves configuring the watermark and window parameters correctly. By effectively managing late data and event time processing, you can ensure the accuracy and reliability of your streaming analytics. Stateful operations are critical in streaming analytics as they maintain intermediate state information across multiple events, allowing for complex computations and aggregations. In Spark Structured Streaming, stateful operations enable you to perform operations like counting, summing, and averaging over a window of time, which are essential for real-time analytics. Implementing aggregations involves defining the state that needs to be maintained, such as the sum or count of events, and updating this state as new data arrives. Sessionization, a form of stateful processing, is used to group events belonging to the same session for analysis. State management in Spark is handled efficiently, ensuring that state information is stored and updated correctly. Real-world applications of stateful operations include user activity tracking and event correlation. By mastering stateful operations and aggregations, you can build powerful streaming applications that provide deep insights into real-time data.
Fault tolerance is a critical aspect of any streaming application, ensuring that data processing continues smoothly even in the face of failures. In Spark Structured Streaming, fault tolerance is achieved through a mechanism called checkpointing. Checkpointing allows you to save the state of your streaming application to a reliable storage system at regular intervals. This ensures that in the event of a failure, the application can be restarted from the last checkpoint, with minimal data loss. Configuring checkpoints involves specifying the checkpoint directory and ensuring that the storage system, such as HDFS or cloud storage, is properly set up. Ensuring data consistency requires careful management of offsets and state information. Practical examples of fault tolerance include handling node failures in a Spark cluster and recovering from network interruptions. By effectively implementing fault tolerance and checkpointing, you can build resilient streaming applications that maintain data integrity and continuity. Apache Kafka is a popular messaging system used for data ingestion in streaming applications. Integrating Kafka with Spark structured streaming offers several benefits, including high throughput, scalability, and the ability to handle large volumes of data. Setting up Kafka integration involves configuring the Kafka broker details, topic names, and other parameters in your Spark application. Handling offsets and partitions is crucial to ensure that data is consumed and processed correctly. Kafka's Consumer API allows you to manage offsets efficiently, ensuring that messages are not missed or processed multiple times. Real-world integration scenarios include ingesting log data from distributed systems, processing social media feeds, and monitoring IoT device data. By mastering Kafka integration, you can build powerful streaming applications that leverage the strengths of both Kafka and Spark.
Monitoring and debugging are crucial aspects of maintaining the health and performance of streaming applications. Monitoring involves tracking key performance metrics, such as throughput, latency, and error rates, to ensure that your application is running smoothly. Tools like Spark's Web UI, Ganglia, and custom dashboards provide valuable insights into application performance. Debugging involves identifying and resolving issues that arise during execution. Common debugging techniques include examining logs, using breakpoints, and analyzing stack traces. Optimizing application performance involves tuning parameters like batch size and memory allocation, as well as identifying and addressing bottlenecks. Handling common streaming issues, such as data skew and network latency, requires a deep understanding of your application's architecture and data flow. By mastering monitoring and debugging techniques, you can ensure that your streaming applications are reliable, efficient, and performant.
As we conclude our session on real-time streaming with Spark structured streaming, let's recap the key concepts we've covered. We've explored the importance of real-time streaming in modern data-driven applications and how Spark structured streaming provides a powerful platform for processing massive data streams. From setting up a Spark streaming application to understanding sources, sinks, and handling late data, we've delved into the intricacies of building robust streaming solutions. Real-time streaming continues to revolutionize industries, offering timely insights and facilitating rapid decision-making. As you continue your journey in streaming analytics, I encourage you to explore further and experiment with the concepts we've discussed. The future of streaming is bright, and by mastering these skills, you'll be well equipped to harness its full potential. Thank you for joining us, and happy streaming!